Hi and welcome to this tutorial on why you need to pay attention to material models, which material model you select, how they work, and some of the problems that can occur if you don't pick a good material model for your finite element simulations. I'm going to do this by talking about 4 different examples today. So let's go to the first one. In this example, I'm looking at a chloroprene rubber material. It's a component made of this usual material. I will talk a little bit about what can go wrong if you work with this material. So here we have experimental data, uniaxial compression data for this material. The red curve is the compression data that was measured experimentally. The blue curve is a prediction. It's a prediction from a material model called Aruda-Boy's 8-chain hyperelastic model. We can see that the blue prediction is quite similar to the red experimental curve, and therefore one could think that this is a good model, we're in good shape, we can just use this one in our finite element simulations and expect good results. But is that really the case? Is there something else going on here? What are the problems here? What are we missing, really? So that's something to think about, right? If you go back and think about this a little bit more, you may come up with the idea that maybe you need more data. Here I have additional experimental data for this same material. In this case, I tested this rubber cyclically in compression. So I compressed it, unloaded it, compressed it, unloaded it, which gave me these stress strain loops here. If we now take the material model that we calibrated initially, and we compare that to the new data for the same material, we'll see that the figure to the left here, the red curve is the experimental data, and the blue one is our initial calibration using a very simple hyperelastic model. And what do we see? Well, we'll see that the fit between the experimental data and the material model is not so good anymore. Say at 40% compression, the experimental curve here could be down at 0.75, but in the prediction from the hyperelastic model could be at least twice that. So 100% error in that prediction. Not so cool anymore, right? Clearly this is a problem. On the figure to the right, I am plotting the same experimental data, but predictions from a different, more sophisticated material model. This is the Bergstrom-Boyce-Mullins model. Sounds pretty good, right? This is a model that I've developed many years ago, and it's still one of the absolute best models that are available for rubber-like materials. We can see from this figure, if you look really carefully, that it actually captures the essence of the material response under these conditions. So that's an example of a good model, and something that's much better for you, for your predictions at least, if you were to simulate something out of this material. Second example. These days, a lot of people are very excited about 3D printing, 3D printed materials and parts, and trying to optimize the shape and design of these types of products and components. To do that, you clearly need to have a good understanding of the geometry you print, but you also need to understand the nonlinear response of the matrix material itself. So here is a figure from a paper that I co-authored. We'll see that you can explore different shapes that each fill space for this material. This allows you to simulate the properties of this big block here, and you can optimize that for whatever application you have in mind. But if you want to simulate this, which is really a good way to optimize anything these days, you need to first do some experiments on the matrix material. In this case, it was nylon 12. And you see some tension and compression experiments that I performed here. And we can also see predictions in dashed lines. And the predictions in dashed lines look super good, right? There's such a tight fit compared to the experimental data. How did we do that? Well, we used a sophisticated viscoplastic material model that I call the Flow Evolution Network, FEN model. This is part of the Polymer library. And there's really no way you can get that kind of good prediction unless you use a viscoplastic material model. Once you have that, you can then simulate whatever you're interested in. So here's an example of an experiment on a 3D printed part that's just being crushed from the top. And on the figure to the left is what you can see in an abacus simulation of the same kind of problem. Clearly a good, an interesting tool to be able to do these kinds of simulations, right? All right, let's move over to our third example. In our third example, I'm going to talk about a material called polyether ether ketone, PEEK. So polyether ether ketone is a material that's used in many different applications. It's a high performance polymer. It's used in biomedical applications, among other things. Say you want to simulate a hip implant made of polyether ether ketone. You need some experimental data so you can get the material model and then design and fix your geometry in your product, right? So say you go and do some compression experiments. Here are two compression experiments that are performed on the PEEK material. There are two different strain rates. We see the yield stress changes a little bit with the strain rate between these two tests. But say now you're interested in the performance of this hip implant under impact conditions. Someone is running, for example. What if the strain rate is as high as 1,000 per second? Can we predict, using the data that we have at low rates, what will happen at high rates? Well, I don't know. Maybe we have to explore that. So I went ahead and we did some experiments, and we determined that the properties, the yield stress specifically, is pretty strongly sensitive to the deformation rate, the strain rate that's applied. So this figure shows the two curves from the previous page, and also predictions from, or data from, a really high impact test that was performed on a split Hopkinson pressure bar system. We see that the yield stress changes from about 150 to about 200 megapascals as the strain rates increases, a pretty substantial increase. And clearly very important to know if you want to select and calibrate a suitable material model for this kind of material and this kind of application, right? My last example to illustrate the value of using advanced material models and advanced testing techniques is a soft foam. So here's experimental data for a soft foam. You can see uniaxial compression to very large strains, about 70% strain. Then we unloaded it. We did this at two different rates. The point where the stress strain curve rolls over is not really yielding. These are soft. It's a soft elastomeric foam. It's more of a cell wall buckling initiation of the material. We'll see though that it's a very strong dependence on strain rate here, and we could try to fit a material model to this if we like to, but what if this is a material that we then use in, say, helmets? Helmets are very important applications, of course, of products. And if you have a helmet and you get an impact, you may have strain rates that are much higher than these two, perhaps up to 1,000 per second. So in that case, what do you do? How can you find out what this material will behave like at 1,000 per second? Well, you need to test it, obviously. So in this case, we performed some high-rate impact test experiments using a drop tower, and we measured the stress-strain response in addition to the two slow rates at these really high rates. Look at this. It's unbelievable how different the stress-strain response is at the high rates compared to the slow rates. Clearly, this is something you wouldn't easily predict unless you perform the experiments. One easy way that people often plot these things is to plot the secant modulus as a function of the logarithmic strain rate. And in this case, for this material, there is a transition from two different behaviors because, in fact, this material undergoes a transition in its response from being soft to stiff at the given strain rate. So that's not something you would have guessed unless you tested it. And once you test it, though, you can use advanced material models to predict this kind of performance. So what I wanted to show here in this little tutorial is that it's very important to think carefully about how you test your materials. It's very important then to use proper material models in order to capture those behaviors. And that's really is the focus here. If you have any questions, please head over to polymerfem.com and send me a message. Thank you.